So today I'm going to tell you a story about how your compilers can screw up your code. So for many decades as programmers, we trust our compilers. We think our compilers are very faithful translator that translates our source code into machine instructions that the hardware will execute. Well, this is not actually true if your code invokes something called undefined behavior. So I'll give you some details about this undefined behavior and tell you what's the security implication of this undefined behavior thing. So here is one example. You can find this is a real-world code, and you can find this in a lot of applications like the Chrome browser, the FmpEG decoder, the Python virtual machine, the Linux kernel, the Zen virtual machine. And now I'll explain to you how this code works. So suppose you have a buffer, and there are two pointers, buff and end. That points to the beginning and the end of the buffer, respectively. And now you are reading an untrusted integer off. And now, of course, as a very professional programmer, this programmer wants to verify if this name is too large or not, and try to reject malicious values. So the first case you can see here is that when off is large, and buff plus off exceeds this buffer end. And in that case, the code returns. Another case is when off is really, really large. And in that case, this buff plus off will wrap around and actually end up with a smaller value. So in that case, you can see buff plus off overflows and wraps around to an even smaller value. And you can see the programmer here is also very careful and checks this case. And then the code continues to access this buffer using this off value. The code looks good. However, there's a tiny problem, a not so tiny problem, is that the C specification says pointer overflow is something called undefined behavior. So what that means this allows GCC to say, okay, buff plus off actually cannot overflow. And buff plus off is always larger. And that means GCC can do this, or actually GCC does this, is to optimize this check into a constant false and completely remove this check. So in this case, you can see as an attacker, you can craft a very large off to bypass the only check that remains. And now you can actually trigger a buffer overflow and do interesting stuff here. So you might ask why and what part of the C specification allows the compiler to do this. So here, undefined behavior in the C spec actually is something called, I'm not imposing any requirements on the compiler. So that means if your code invokes undefined behavior, then the compiler can do anything, and that's legal. So why is that useful? So original goal of undefined behavior is to allow a compiler to generate efficient code. So here's one example. Compilers allowed you to simply assume your code is perfect. There's no undefined behavior in your code. And for this simple code, like you are storing 42 into a pointer P. And because the compiler can assume, fine, your code is fine, there's no buffer overflow. So I don't have to generate any buffer overflow or any bounds checks. So there's only one single move instruction. That was useful. But here are some very unfortunate consequences. These are some meaningless checks from real-world code. Here P is a pointer, X assigned integer. In the first example, you can see the check is if P plus 100 is smaller than P. This can be true only if you invoke undefined behavior, and this check actually is meaningless. So you can see similar checks like signed integer, shifting, and non-pointed reference. It's worth noting that even some library functions have undefined behavior, like this ABS function in the standard C library that computes the absolute value of an integer. And if you do a check like this, it's still undefined and meaningless. So in this talk, I'll focus on this problem we call unstable code, where compilers discard your code due to undefined behavior. And this has serious consequences. You can see your security checks are gone, and a minor bug is optimized into a major vulnerability. And this is very frustrating to programmers because you will end up with an unpredictable system. So here's the agenda for the rest of the talk. I'll show you a case study of unstable code in real world. I'll show you a new algorithm for identifying unstable code. Also, I'll introduce our static checker for unstable code called Stack. We have used this tool to find 160 previously unknown bugs from a bunch of open source projects. All of those bugs were confirmed and fixed by the corresponding developers. And also now we have some users and developers basically from Intel and several open source projects. So to start with, I'll show you another example from the Postgres database. So imagine now you implement a 64-bit signed division, x over y, in SQL. What should you do? So as a good programmer, you know, okay, first, you don't want to do division by 0, then y cannot be 0. That's simple. Another case is actually signed division could overflow. So there's a case when the divisor y is -1 and x is -2263, and the result is not representable in the 64-bit integers. So the programmers wanted to check for that case. So here's the actual code from Postgres. You can see it's a very twisted form. Try to see if this is overflow case. Does that even work? Unfortunately, there are some consequences. So one case is for some compilers, this check actually will be gone. You get nothing in the resulting binary. And also, even some compilers don't optimize away this check. On x86, this 64-bit division instruction traps overflow. So you can crash the database server without this select thing. So that's actually how we did to this, showed to this Postgres developers. Of course, we also proposed a fix. So the fix is simply straightforward to just check if x and y are those values. Well, the developers have their own taste. They hate constants. And they say, if you're doing overflow, you should do like overflow. So they also change our proposal to this another twisted form. And GCC actually is fine. This time GCC won't optimize away this check, and you will not see any crash. But this is still unstable code. So it's possible that future compilers will also optimize this code away. So this is this frequent change, this is unpredictable change of compilers optimization causes a lot of trouble or some tension between programmers and GCC developers. So here is one example from a very angry GCC user. He claims, you guys are creating major security issues of the place. I don't care what the language lawyer says, just fix your broken GCC. And of course, GCC developers fall back. So your code is broken. We are fine. Go fix your code. So is that actually a GCC thing? So to make sure that, we test a bunch of popular C compilers. So here are some compilers you might use, like two open source compilers, GC and Clan, and a bunch of commercial compilers from big companies. And to test how they behave, we use the 5 unstable examples from the previous slide. So if a compiler is aggressive, it will turn this check into a false. So it will basically optimize away the entire check. So, and here is the result. So the first row is the 5 unstable code examples. And the first column is the 12 compilers. If a cell is green, that means the compiler generates code as is. So nothing happens. If a cell is red, and that means the compiler kills the check completely. You get nothing in the result system. So here you can see it's pretty common for compilers to do crazy things. And they do this at different optimization levels. So to see when did compilers start to become so advanced and so aggressive, we also look at the history of 2 open source compilers because their history are easily accessible. So the first one is the very old GCC, like GCC1, which was released like over 2 decades ago. And it's similar to human beings. You are more innocent when you are young, and you do more damages when you grow older. And you can see as GCC time goes by and until this latest GCC release this year, and you can see it's pretty aggressive. And also you can see a similar trend in Clan 2. Like the very first version was okay, and then now it's really advanced and aggressive. So there are two observations from those results. So first, compilers silently discard your code, and that's very frustrating. A second observation is different compilers behave in different ways. So it's very hard for programmers to predict what would happen. So one day if you change your program, you change your compiler or you upgrade your program compiler, and you get a different or broken system. So we need a systematic approach to deal with this issue. And here it is. So our approach is to precisely identify unstable code using our tool called Stack. And here's how you can use it. So first, you just configure your projects as you roll. Then you prepend our script stack build to your make command. And in this case, our script generates LLVM intermediate representation. And then you run our script to generate warnings against your code. And here is a sample output for this Postgres example I have shown you before. You can see our output is very informative. You can see our tool basically says, okay, I could optimize this check at line 2 into a constant false and remove it because you have an earlier division at line 1, and it explains to you which undefined behavior is evoking and what's the reason. So how does our tool generate such warnings? So I'll give you some high-level ideas of how our tool works. So the first question we want to ask is, what's the difference between compilers and some programmers? So we think this actual assumption denoted by delta is this actual assumption a compiler knows, that is, programs don't invoke undefined behavior. So compilers assume programs are perfect. They don't write code that invokes undefined behavior at all. Then what can compilers do with this actual data? Now, of course, they can optimize away unstable code. And then how Stack works is basically to mimic a compiler, a very aggressive compiler, but it can selectively enable delta. So it works in a two-phase way. In the first phase, it optimizes code without delta. Then it does the same optimization again, but this time with delta. Then the difference between the two phases would be unstable code. So I'll show you one example. This is still this Postgres example. The extra assumption here is that you don't do division by 0, you don't do division overflow. And Stack, in the first phase, Stack asks, can I optimize this? Is this check res less than 0 equivalent to false? Can I optimize it away? Of course, the answer is no. You cannot do it. It's not equivalent. But with this actual data, now Stack asks again, can I do it now? And the answer is yes. And then our tool reports a warning. So how do we compute this assumption data? So here's the detail. So the intuition here is that if you have a very, very good program, then okay, one must not trigger undefined behavior at any code location, like any code fragment. So to compute this, we have two properties for each code fragment. The first one called reach. It's a Boolean expression under which you can reach and execute a code fragment E. Another one is undef, which means you can trigger undefined behavior under this Boolean condition. And the intuition is if you have a rich condition, that can be true, then the undef condition must be false. Okay. So here is how we can compute it. So this is still the Postgres example. At the first line, you know the rich condition here is simply true, and the undef condition is divisor could be 0, or this could be overflow. That's the undef condition for line 1. For line 2, it's easy. The rich condition is still true. There's no undef condition at all. For the third line, this return. The rich condition here is more complex, basically the if condition. And then this here, there's no undef condition, so it's simply false. So you just merge them together and do a logical AND, and you get this final result. That's delta. So now stacks use delta to do a two-phase detection. So in the first phase, it now asks the solver, like, is this check equivalent to simply a false? Here, like in the first phase, stack doesn't use delta at all. So the answer here is no, it's not equivalent. So stack moves on to a second phase. And in the second phase, it now assumes this delta can be true and asks the question again. So can I optimize this to false? Is that equivalent? And the solver says, OK, yes, this is true this time. And stack reports, OK, here's unstable code. This check is unstable. So that's how our tool works. To sum up, so the first step is to compute this extra assumption, delta. That is, your program never invokes undefined behavior. Then it conducts a two-phase detection without and with delta, and the difference is this unstable code. There are some limitations of this approach. So if this phase 2 is not powerful enough, then you may miss some unstable code bugs. If the first phase is not powerful enough, then you can have false positives. We implement this tool using LLVM and deep blue lecture solver. It's roughly 4,000 lines of C++ code. For better scalability, we simply do a per function analysis. So you can imagine we could miss some bugs due to this cross-function environments. In the next, I'll show you some evaluation results. Is our tool useful for finding unstable code? Or how precise are the warnings? And how prevalent could be out there is unstable code? And how much time does it cost to analyze a large code base? And here are some software packages we have found unstable code in. You can see that our tool is useful for finding unstable code, and we have used this tool to find over 160 new bugs. And to understand what's the false positive rate, we manually inspected two packages. One is Kerberos, another is Postgres. For Kerberos, our tool produced 11 warnings. The developers took every one of them and fixed their code. And after that, our tool reports nothing, so 0 warnings. So in that case, our tool has no false positives. For Postgres, it's slightly different. We first report some bugs, and the developer said, we are fine, we write perfect code, and your tool is wrong, or the C compilers are wrong, just blame them, fix their compiler. So refuse to fix any bugs. So we demonstrate how to crash their server and say, OK, fine, we're going to fix 9 of them. For the rest, it's still actually like some compilers optimize away their security checks. So you can try to play around their server, the exploit out there. And for some of them, like 26 of them, like we haven't found any existing compilers that could optimize away those checks, but it could be in the next few years. So let's see. For this case, we have 4 false warnings. So you can see the false warning rate is pretty low. It's 4 out of 68. So it shows our tool is practical and it's easy to use in practice. To understand how much unstable code could be out there, so here's an estimation. Because our tool has a low false positive rate, so you can see we can use the warnings to estimate. And we applied our tool to all Debian packages. There are over 8,000 packages that contain C and C++ code. We find unstable code warnings of around 40% of them. So this is a hint of how prevalent unstable code could be. Here are some performance numbers. We run our tool for 3 code bases: Kerberos, Postgres, and Linux kernel. And you can see even for a very large code base like the Linux kernel, it takes roughly 1.5 hours to finish analyzing all the source code. So it shows it's practical to use our tool once in a while, like maybe every day or once a week, to check for unstable code during your development cycle. So because unstable code is a serious problem, so how do we fix them? How do we avoid them in general? So for programmers, of course, the best way is to fix your code. And also, there are some compiler workaround options. You can try to disable certain optimizations. For compilers and checkers, so first, you have to model C correctly. It's actually trickier than you expect. Many bug finding tools actually do this wrong. And we hope that they can adopt our ideas to generate better warnings against unstable code. For language designers, we hope they can rethink, like, do you really need undefined behavior at all? Like, do you really care performance here? So for them, I think they should rethink about this undefined behavior because we have shown these serious consequences. There could be other applications. Our evaluation of unstable code shows this new instance of reflecting on trusting trust case, like how trust your compilers could be. Suppose you work for some government agency, and your job is to inject backdoors into open source projects like the news kernel. You have a good pay, and from time to time, you can have free trips to Hong Kong and Russia for a long time. So what can you do? So you can submit like a new driver to a news kernel with unstable code intentionally. And because a lot of bug finding tools, except ours, do this wrong, and also many programmers misunderstand unstable code. So it's easy actually relatively easy to inject unstable code into open source projects. So it's just warning. I'm not encouraging you to do it. Just be sure someone could do it. So to sum up, unstable code is some kind of subtle bugs, and it has significant security implications. So for compiler writers, we hope they can use our techniques to generate better warnings. And for language designers, we hope they can rethink the trade-off between performance and security. And for programmers, we encourage you to download our source code from here. Okay, thank you.
Hi, Brad Karp, UCL. I really enjoyed your talk. I think one thing I wanted to ask about is, I don't think it was mentioned in the talk, is when you run the solver, I think you say in the paper that you have a timeout, right, because sometimes solving can take a while. And you chose a value for the timeout in the paper. But one thing I was curious about was, obviously, presumably, you would choose the timeout to be some kind of sweet spot, right? Because maybe if you waited a little bit longer, you would have caught a lot more bugs or something like that. But at the same time, you also said in the paper, if you want better results, you can just run the solver for longer. So how do I reconcile these two things? Like, what is the distribution of solver time? Have you tried different solver times, and would running longer actually find many more bugs or not?
So the question was how to decide timeout for solvers. So actually, during the development, we tried a bunch of timeouts. First is 1 second, then we increased to 5 seconds. Then we actually didn't see, we actually increased to 30 seconds when we didn't see much change anymore. So we just stick to 5 seconds. So that's how we did it.
Thank you.
Yeah.
Okay, let's take a Dear Abby question. How hard is it for the compiler, for example GCC, to implement similar functionality as stack? I think the compiler should have a good and probably more thorough knowledge of what the specification is, and if a code construct relies on undefined behavior.
So the question was how product compilers could adopt our techniques. So I have two suggestions. The first thing is, for practice, our tool basically doesn't really care about performance that much. For real compilers, you want to finish compiling your code within 1 second or 0.5 seconds, and that's pretty critical for a compiler. So compilers' algorithms are simpler. For example, it's probably compilers probably don't want to adopt solvers, so you probably want a simpler decision procedure, you only do range or simpler thing. Another point I want to raise is because you can use some simplification, and that means you will miss some bugs. So even GCC doesn't do it. This has a drawback. So if GCC doesn't report this warning, then client actually probably optimize the code away. So there is a trade-off between performance and precision. So that's my suggestions.
Thank you. Eric?
Hi, I'm Eric Ide from the University of Utah. I was wondering if you've experimented with interprocedural analysis, or if you had any intuition about additional undefined behavior that you might find through interprocedural analysis, if you were willing to do that.
So the question was there could be additional undefined behavior, and also there could be interprocedural, this new, more advanced algorithms. What actually we do is to invoke LLVMs inline. So we do inline first. That helps with interprocedural analysis. Then we do a per function analysis. For other undefined behaviors, there are actually interesting cases. One is data race. Like we didn't address this problem. So with data race, you can reorder instructions due to different memory models. And there was a good paper like in HotPar about like how compilers actually could screw up the code if you write like some sort of like data-free code, data race-free, log-free code, and actually it's wrong. So that would be interesting to see.
Thank you.
Thank you. Okay, here's another question. If buff plus off less than buff evokes undefined behavior, what's the correct portable and optimization safe way to check for large offsets that incur rep?
So the question is how not to invoke undefined behavior. The first option is not to use C. That's not so practical. There are two suggestions actually. In the original, like this was several years ago in the vulnerability note, the suggestion was you can cast pointers to unsigned integers. So if there is or signed integers, there is a type in C, it's called int ptrt, so you can do that. That's perfectly fine. Another trick you can do is don't use addition, use subtraction. You can do math and buff and minus something, and that's also legal.
How about just checking for off less than size of the buff?
Yeah.
Okay. How about you?
Hi, Matthew Fernandez from NICTA and UNSW. Did you find any unstable behavior in GCC?
Yes, we do. I can show you the link later. Yes.
Thanks.
We can trigger it.
Oh, excellent.
So, I'm thinking if I'm a developer, right, I'm writing code, I already have to send it to a code review system. Probably have to run lint on it, do a bunch of other things. And now I have to run another tool on my code, right? Can you comment a bit on how to integrate this better into like a developer's workflow? Because I'm afraid what's going to happen is that even if this is really useful, people just aren't going to use it because it's just that extra one thing they have to do, and it's already really painful, right? So I was just kind of curious if you had thoughts on this.
So I have some speculations, but I think like large companies have some disciplines. So one example is like in Microsoft, in Google, like you have like tools when you're checking code, actually the tools were wrong. And every night they will run tools too, and you will receive like a notice, a report.
And then you spend hours fixing the output from those tools, right? So it just gets more and more painful, I guess. Right?
Well, I think one way also they can increase our programmers' salary, so we are willing to fix more bugs.
Yeah, there we go. I like that. Okay, I like that answer.
Stefan?
So Stefan Savage, UC San Diego. So I have a follow-up on that. I thought this was really neat work, and one of the things that seems cool is I suspect you can probably automatically generate a solution that is consistent with what we expected the semantics to be. But taking a step back, right, 10,000-foot view, we've got all these different kinds of bugs. We have the bugs where the programmer doesn't understand the correct semantics, right, and basic integer overflow and the difference between free and free of an array in C++, gazillions of things. And so, Dawson and company will sell us a checker for that. And then we got this stuff where, well, there's a dispute between the implementation of the compiler and the implementation of the specification, and we have another checker for that. And then we've got this stuff where the specification and the implementation of the hardware, like the goddamn Java memory model, isn't quite right, and we need another checker for that. And I will tell you, if you repeat your experiments and instead of looking for undefined behavior, look for corner cases and common optimizations across those compilers, you will find a whole other set of bugs where now the compiler is wrong with respect to the specification, but people get, and we're going to need another checker for that. And so taking a step back is the right answer that we should identify an ever greater number of ways that the spec writer, the programmer, the compiler writer, and the optimizer have all not agreed on what the program is supposed to do and come up with checkers at every interstitial space? Or do you have any thoughts about another way of going at this that doesn't require me to know what an int pointer 64 type is that no one here has ever learned? Okay, so this is a very deep question. So I think basically
it's equivalent to how do we resolve like human conflicts in the past 5,000 years. Yeah, I don't know. I think it's very deep, and it could be like 10 PhDs out of it. Yeah, I think it's great. We can talk offline about this.
So we've had question from the microphone, we've had question from cyberspace. There's one group of people I forgot to ask for questions, the speakers. Are there any questions from the speakers? Oh, you have a question?
Yeah. Thanks. Okay, thanks for the great questions. And also, I have a question for you. If you still want to program in C, this is some code from a CPU emulator from a very well-known company. The developers shared the experience with us. So the code implements 16-bit multiplication. So you can see it's very simple, just one line of code. And every type is unsigned, make sure. And you try to emulate 64-bit multiplication again. So the question is, what's the result of this code? A or B or C using GCC on x86. That's simple. So just if you have some thoughts, like we can talk during the poster session. Okay, thank you.